Hello everyone, my name is Ismail. Today I'll be presenting our work called PuDHammer, Experimental Analysis of Read Disturbance Effects of Processing using DRAM in Real DRAM Chips. Let's start with an executive summary. So processing using DRAM is a promising paradigm to elevate data movement bottlenecks between main memory and computing units. And prior work showed that DRAM can actually perform many processing using DRAM operations, such as AND and OR, by activating multiple DRAM rows in quick succession or simultaneously, which is also called multiple row activation. However, DRAM is subject to read disturbance. Repeatedly activating even a single DRAM row causes bit flips in other unaccessed DRAM rows. And the problem is, no prior work studied the read disturbance effects of multiple row activation. And our goal is to understand and analyze the read disturbance effects of multiple row activation. And to this end, we conduct an experimental study on 316 DDR4 chips from 4 major manufacturers to study this effect, which we call PuDHammer. PuDHammer significantly exacerbates DRAM read disturbance, causing up to almost 160x reduction in minimum hammer count to induce first bit flip. And PuDHammer bypasses in DRAM RowHammer mitigation employed in DDR4 and induces much more bit flips than RowHammer. And to prevent PuDHammer bit flips, we try to adapt per row activation counting, the industry's latest solution to RowHammer. And we observed that adapted solution incurs an average system performance overhead of almost 50%. So here's the outline of my talk, and I'll start with a brief background. DRAM module is organized with multiple DRAM chips, and inside the DRAM chip, we have multiple DRAM banks. Inside the DRAM bank, we have multiple subarrays, and within each subarray, we have two-dimensional array of DRAM cells. A row of DRAM cells called DRAM row, and they are connected through word line. A column of DRAM cells connect to sense amplifiers via bit lines. And there are 3 major DRAM operations that we focus. First, activate command, which fetch row contents into sense amplifier, and then column accesses such as read and write, and precharge to prepare the bank for a new activate. Until now, we see that DRAM is just used to store data. And this is because today's computing systems are processor-centric. All data processed in the processor at a great system cost. In order to compute, you need to move the data back and forth between main memory and computing units. And prior work showed that more than 60% of total energy is spent on this data movement. And processing using DRAM is a promising paradigm to elevate such data movement bottlenecks. It uses analog operational principles of DRAM cells to perform computation. And multiple row activation is a key technique to realize many processing using DRAM operations, such as AND and OR. And we categorize this multiple row activation into 2. First, consecutive multiple row activation. Second, simultaneous multiple row activation. The key observation of consecutive multiple row activation is violating timing of precharge command in off-the-shelf DRAM chips activates 2 rows consecutively. Here we have a DRAM subarray which consists of many rows including SRC, source, DSD, destination. And if we obey the timings between activate, precharge to precharge and activate, we only open a single DRAM row at a time. However, if we violate the timing between precharge to activate destination, we will activate destination without deactivating the sense amplifier nor the bit lines. As a result of this, we copy source content into destination, which is in DRAM row copy. And for simultaneous multiple row activation, the key observation is activating 2 rows in quick succession simultaneously activates multiple rows in a subarray. Here we have an example subarray that has row A and row B. And again, if you obey the timing parameters, we will activate a single row at a time. However, if we violate both timings between activate to precharge and precharge to activate, we observe that we can activate many DRAM rows at once, simultaneously. And one example for using SIMRA is realizing in DRAM majority of 3. Assume that we have act per act, again, this command sequence, and we have 3 rows that we activate them simultaneously, which assert these 3 rows word lines. And after that, 3 rows perturb bit lines simultaneously. Due to charge sharing, sense amplifier will sample the output of majority of activated rows. In this case, it's B. Unfortunately, DRAM is subject to read disturbance. Even activating a single DRAM row disturbs the data integrity of other unaccessed row. And a prominent example for that is RowHammer, where we keep repeatedly activating and closing a one DRAM row causes bit flips in adjacent rows. We call hammered row as the aggressor row, and the victim rows as the rows that experience bit flips. And this phenomenon brings us to our problem and goal of this paper. No prior work investigates the read disturbance effects of multiple row activation, and our goal is to understand how multiple row activation affect read disturbance vulnerability. And to experiment with DRAM chips, we build a real DRAM chip testing infrastructure. This infrastructure enables us to have a fine-grained control over DRAM commands, temperature, timings, and voltage. And in our lab, we have many machines to test many DRAM modules and chips. And we test a total of 316 DDR4 chips from 4 major manufacturers. And we cover different die divisions and chip densities. And now let's move on to our first analysis, read disturbance effects of consecutive multiple row activation, which is activating 2 rows consecutively. To hammer using this COMRA access pattern, consecutive multiple row activation, first we have double-sided, where we sandwich a victim row. To adapt this to COMRA, what we did is we copy source to destination to sandwich a victim row. And for single-sided, where we hammer only a single row and induce bit flips in adjacent rows, we copy one row to another which are far away from each other. And to characterize the read disturbance vulnerability, we carefully sweep row addresses, timing parameters, data pattern, and temperature. And to assess the read disturbance vulnerability, we use a metric called HC first, the minimum hammer count required to induce first bit flip, and lower is worse. And here we have, again, double-sided scenario for consecutive multiple row activation, and we count one hammer as one consecutive multiple row activation operation. And between each hammering, we obey the timings and issue per charge command. And then, after enough hammering, we record the bit flips in the victim rows. Now, let's see our first result, comparing double-sided consecutive multiple row activation versus RowHammer. And the x-axis, we have the manufacturers, and the y-axis, we have the lowest HC first that are observed from each manufacturer, and each color represents different operation. And we observed that for SK Hynix, the reduction is almost 14 times. And this reduction in lowest HC first is consistent across all tested manufacturers. And in this experiment, in the second experiment, we would like to understand how each victim row behaves under double-sided COMRA versus RowHammer. In the y-axis, we have the HC first change. The x-axis, we will have the DRAM rows sorted by reducing HC first changes. And each line will represent the manufacturers. Now let me walk through this plot. So P1 to P100 represents 99% of tested victim rows. Similarly, P50 to P100 represents 50% of tested victim rows. And negative HC first change means COMRA reduces HC first compared to RowHammer. And for example, HC first changes of minus 50 means RowHammer HC first is 100, COMRA HC first is 50 as an example. And we observe that more than 99 of tested victim rows experience lower HC first, which is doubles, and we conclude that double-sided COMRA decreases HC first for a large fraction of rows compared to double-sided RowHammer. And these experiments, using these experiments, we conclude that COMRA exacerbates DRAM's vulnerability to read disturbance in all 4 major manufacturers. Here, now let's see the simultaneous multiple row activations effect. Recall that this activates multiple rows simultaneously. And again, the characterization methodology is the same as previous one. We sweep row addresses, timings, data pattern, and temperature. And now let's see how it behaves compared to RowHammer. And the x-axis, we have the simultaneously activated rows from 1 to 16. 1 represents RowHammer. And in the y-axis, we have the lowest HC first. And we observe that reduction in lowest HC first is almost 160x. And for the other number of tested simultaneously activated rows, the reduction is similar. And when we look at each victim rows behaves, again, more than 99% of tested victim rows experience lower HC first, and at least 25% of tested victim rows experience more than 99% of reduction in HC first. And we conclude that double-sided COMRA significantly decreases HC first for a majority of rows compared to a double-sided RowHammer, and which translates to COMRA drastically exacerbates DRAM's vulnerability to read disturbance. So we saw that the effect is severe. So how do we mitigate that? Or what can we do? Now we take a two-step approach. First, we analyze the effectiveness of existing in DRAM RowHammer mitigation employed in DDR4, TRR, against PuDHammer. And second, we try to adapt RowHammer mitigations to account for PuDHammer bit flips. Let's see the first one. First one is target row refresh, which DRAM vendors equip their DRAM chips with a proprietary mitigation mechanism known as target row refresh in DDR4. And the key idea is TRR refreshes nearby rows upon detecting an aggressor row. Here we have a pictorial example of the system. We have memory controller and TRR-equipped DRAM chip, and assume that TRR detects row 2 as an aggressor. And upon a TRR-induced refresh, it will refresh neighboring rows, which are row 1 and row 3 in this example. So we test real DRAM chips to see the effectiveness of TRR for RowHammer, COMRA, and SIMRA, and we observe that first without TRR, and we test different number of aggressor rows, basically different memory access patterns, and the y-axis shows the total bit flips. We observe that without TRR, RowHammer induces more than 10,000 bit flips in the worst case. However, with TRR, we observe that the bit flips reduction is huge. It's less than 60 bit flips in the worst case pattern. And for COMRA, it's very similar to RowHammer. Without TRR, it induces 10,000 bit flips, and with TRR, it's around 60 bit flips. So we conclude COMRA induces 1.10 times more bit flips than RowHammer on average in the presence of TRR. So now let's see this simultaneous multiple row activation, SIMRA. So without TRR, it induces a lot of bit flips, 240,000. With TRR, it still induces a lot. It's 180,000 bit flips. And on average, SIMRA induces more than 10,000 more bit flips than RowHammer. And we saw that TRR is not effective against SIMRA and COMRA as RowHammer. And we try to adapt RowHammer mitigations to account for PuDHammer bit flips. And we chose PRAG to show an example here. And we take, again, two approaches. One is a naive approach that you reduce RowHammer threshold to SIMRA's lowest observed threshold, for example, 4,000 to 20. And the other one is weighted counting. You increase each PRAG's counters based on the vulnerability caused by the operation RowHammer, COMRA, and SIMRA. For example, RowHammer, normal DRAM activation will increase the counter by 1, SIMRA will increase 100. To evaluate these two mitigations, we use Remulator 2, a cycle-level DRAM simulator. Here's the system configuration. And we use 60 multi-program workloads, each mix composed of 4 workloads from 5 major benchmark suites and 1 synthetic workload that periodically performs processing using DRAM operations. So let's see the weighted speed-up results. And the x-axis, we have PUD intensity, and from left to right, PUD intensity increases, meaning, for example, 125 means DRAM performs processing using DRAM operations in every 125 nanoseconds. And the y-axis, we have normalized weighted speed-up, normalized to no RowHammer mitigation. And we observe that the weighted counting great lot performs in naive until 2 microseconds. However, once we have a greatly increased PUD intensity, weighted counting incurs a lot of overhead, and on average, it incurs almost 50% of performance overheads. We have a lot more analysis in the paper, more characterization results, temperature, spatial variation, timing analysis, access pattern, etc. And we have the combined read disturbance effect of RowHammer with processing using DRAM operations. We observe that the combined access pattern using RowHammer with COMRA and SIMRA is more effective than RowHammer alone, and it reduces HC first by 1.6x. And we have a lot more detailed analysis on mitigating PuDHammer. We discuss how modifying DRAM chips could help mitigating this effect, and more details on PRAG adaptation, like challenges on adapting PuDHammer and the area-efficient PRAG solution, and so on. Our paper is available on arXiv. You can use this link to get the paper, and let me conclude my talk. So we extensively studied interaction between read disturbance and multiple row activation, and we test many DDR4 chips from 4 major manufacturers, and we observed that multiple row activation, PuDHammer, significantly exacerbates the read disturbance vulnerability. It bypasses in DRAM RowHammer mitigation, and it induces much more bit flips than RowHammer. And we adapt per row activation counting for PuDHammer and we observed that it incurs almost 50% of average system overhead. And we conclude that we hope and expect our findings guide system-level and architectural solutions to enable read disturbance resilient future processing using DRAM systems. Thanks a lot for your attention. I'm happy to answer your questions.